Okay. So I'll give your papers back in a little while. So so we've been looking at this idea of the comparison, in some sense, of Eulerian graphs to Hamiltonian graphs. So, one contains all the edges, and one contains all the vertices. And the one that contains all the edges, it's an easy criteria that tells us when it's Eulerian. Just appease me, and that would be connected.
Bipartite with
What was that?
bipartite
Bipartite.
with the same element.
Same in it.
Perfect.
Okay, so
Perfect.
you're talking about Hamiltonian. I'm still at Eulerian.
Sorry.
Okay. The condition for Eulerian.
Even order.
Even
degree.
Even degree. Yes.
even degree at every vertex.
Yeah.
Okay. More than just having an even number of edges. Which even degrees don't guarantee that. So we need some condition. So I've asked you. You've looked at PM and PN. Any thoughts on when that's Hamiltonian? And when one or both are even. Is that right? Okay, so if M and M are even. And in fact, I think that's one of the problems that I assigned for homework, I believe. Okay, by the way, there's a new homework up. I have some other homeworks and I have the test. So we need some condition on, so Eulerian is easy. I'm going to put quotes around easy. Easy meaning all I have to do is look at the degree at every point, decide whether the graph is connected, and if there's any odd degrees, then we know it's not Eulerian. If there is two odd degrees, then we know that it's semi-Eulerian, as long as it's connected. And if all the degrees are even, then we know it's Eulerian. Okay, so those are easy things to check. Hamiltonian is just not so easy. So can you find, so I want to find graphs with, I'm going to put quotes around it, a lot of edges. Okay, and before I go on, you kind of think as I put more edges into the graph, the likelihood that the graph is going to be Hamiltonian goes up. Keep on putting edges in, eventually you'll be able to get all the way around. So can you find a graph with a lot of edges that's not Hamiltonian? So take a minute. Can you find such a graph? Of course, I'm not telling you what I mean by a lot. Do you have homework due today?
No.
Okay. Then there's homework that's due after break. I figured you needed some graph theory to do over break. And that was posted, and it's due the Tuesday right after break,
通点定义是
I think.
不是 Eulerian 是 Hamiltonian，就是 bipartite， 然后不相等 ，complete bipartite。
不是吧？它那个 bipartite 只是它一种情况。
是吗？不是只有它是相等的，然后 complete bipartite 的时候才可以，还是那种 complete bipartite， 然后
应该是 complete bipartite， 它一定是 Hamiltonian， 但是 Hamiltonian 不一定。
So just while you're thinking about this, if I have a graph on n vertices, what's the maximum number of edges I can have on that graph? N choose 2. Okay, so the max number of edges is n choose 2. Can you get close to n choose 2,
80
whatever I mean by close, can you get close to n choose 2 and not be Hamiltonian? Yes?
Yes.
You think so? What graph would that be?
Complete graph. N choose 2, right?
So, wait a second. I heard complete.
Yes.
Complete what? No, you don't want
I don't know.
to?
On n vertices.
A complete what?
On n vertices.
A complete graph on n vertices? Well, that would be Hamiltonian.
Yeah, but then another vertex.
Oh, wait, what? So let me keep our number as n. So if I take a graph, I start with a complete graph on n minus 1 vertices. How many edges are here? How many edges are here?
N minus
N minus 1 choose 2.
N minus 1 choose 2. That's a lot of edges. Okay, so we need one more point. Okay, is this graph Hamiltonian? No.
No.
Okay. And in fact, is this graph Hamiltonian?
No.
No, that's not Hamiltonian either. So in fact, I can get up to almost n choose 2 is the total possible number of edges that I can have on a complete graph. So I can remove n minus 2 edges. That's a lot of edges. I mean, think about what is let's see, 12 choose 2 minus 10. Just 12 choose 2 is 12 times 11 divided by 2 is 66. 66 minus 10 is 56. 56 edges on 12 vertices. That's a lot of edges. So in fact, it's kind of disappointing that I can have a lot of edges and still not be Hamiltonian. Okay, but if I add one more edge, of course, one more edge, and then I'm there. Okay, but we need other results. I mean, this is just that's just a little too much to ask. There aren't too many graphs with this many edges. So when this is like 100, this is 100 choose 2 minus 98. 100 choose 2 is a huge number. So this would be a very dense graph. Okay, and it would be not Hamiltonian. Okay, so I'm going to prove. I want to prove actually 3 results about how many edges that I can add to put a condition on a graph that will give me a Hamiltonian graph, that will assure that it's Hamiltonian. So I'm going to do that in a second, and I think what we're trying to get to, so a complete graph and an extra vertex, if I look at a complete bipartite graph, and let's see, this is M, and this is M. Let's make this M plus 1, and this M minus 1. Why do I want to do that? So I have 2 M vertices. Okay, here I have a big dense piece, and just one edge. A big dense piece and one edge. So I have a vertex of low degree. Here I have, at least all my vertices have pretty high degree. What's the maximum degree in this graph? I mean, that's a complete bipartite graph. What's the maximum degree? Maybe we should just, what are the degrees? What are the degrees downstairs? What are the degrees of these points down here? M plus 1. What are the degrees of these up here? M minus 1. So that's pretty high degree. and yet it's not Hamiltonian. Okay, so all the points have pretty high degree, about half the number of vertices. And in fact, I mean, here I have, these points have high degree, but this has very low degree. Okay, and just to, I can even add more edges. I can make that complete. So I can add a lot of edges and still not have a Hamiltonian graph. So I need to have some sort of condition that goes for the whole graph. So this is pretty close. It's pretty close to how long a path, how long of a cycle can we get here? What's the longest cycle here? Let's look at a small example. Like m is 3, so on the top I have 4 vertices. What's the longest cycle in this graph? 4 out of 6. Let me add a vertex. Let me add another vertex. Okay, again, this is not Hamiltonian. Okay, so what's the longest cycle here? 6. And if I keep doing this, now what's the longest cycle? 8. What's the longest cycle here?
2 times n minus 1.
2 times the quantity n minus 1. So I have a cycle that's pretty long. I have 2 endpoints, and I have a cycle that's of length 2n minus 2, but it's not everything. Okay, so we can force there to be a lot of edges, yet we can't assure that it's Hamiltonian. Okay. So I actually want to prove a result about when a graph is Hamiltonian. So I'm going to prove 3 things, I think. Somewhere, here it is. Bless you. Okay, so let me they don't define this. A graph is Hamiltonian if it contains a Hamiltonian cycle. So they don't use this word, a graph, but I tend to use it. A graph is traceable if it contains a Hamiltonian path. Hamiltonian path. And what do I mean by a Hamiltonian path? A path with all the vertices. So I want to build up to a result that will tell us that given a certain condition, the graph is Hamiltonian. Okay, so it's a minimum degree condition. So unfortunately, it does force there to be a lot of edges. And again, there are Hamiltonian graphs that don't have a lot of edges. There are Eulerian graphs that don't have a lot of edges. But to imply that a graph is Hamiltonian, we have to force a lot of edges in. Okay. So here's theorem 1. And we haven't used this too much. Little delta of G. What's the little delta of G? The minimum degree. Okay, so just to remind you, this is the minimum degree. If the minimum degree of the graph G is greater than or equal to n minus 1 over 2, then G is connected. Okay, so I want to prove that first.
我说这种再看才发现。
比起来应该
So just take a minute. Is that so? I've got a lot of. Is it clear? So I have every vertex is adjacent to nearly half the other vertices. Actually, it's adjacent to exactly half the other vertices, at least. But the graph is not connected. Okay, so here's the proof. Suppose not. Suppose G is not connected. Suppose G is not connected. Then what does it mean to be not connected? What does that mean?
There's two vertices that don't have a path between
But
them.
there's two vertices that don't have a path. So in other words, there are at least two, and this is kind of redundant, disconnected components. There may be more, but I know that there's at least two different components, two pieces that are not adjoined to each other. So here they are. Now, what's the total number of vertices in this graph? How many vertices do I have in this graph? Sorry. Let's make sure we have that down. G has order n. So I have n vertices in this graph. And again, what I want to show is if the minimum degree is at least n minus 1 over 2, then G is connected. Okay? And to do that, I'm going to prove by contradiction. Suppose it is not connected. Suppose it's not connected. So I have at least two pieces. I might have more. I don't know. I don't know how many pieces I have. But suppose if it's disconnected, there's at least two. These are the biggest two. These are the biggest two. So what can you tell me about the size of the second one? Okay, so this is the biggest one, B. And this is the second biggest one. Can you tell me about how many vertices? Can you tell me a bound on the number of vertices in the second largest component? Can there be n over 2? Well, there could be n over 2 here and n over 2 here. Okay, so number of vertices is, but I know that it's the second largest, so it's less than or equal to n over 2. Can't be more than n over 2, because if this was more than n over 2 and this was more than n over 2, I got more than n vertices. And I'm starting with a graph of order n. Okay, so I have less than or equal to n over 2 vertices. So I'm going to choose a vertex. Choose a vertex x. This blue blob has at most n over 2 vertices in there. Could have fewer, but it has at most n over 2 vertices. What can you tell me about the degree of x? This is x right here. What can you tell me about the degree of that vertex? Can it be n?
No.
Can it be n? No, why not?
If it's connected.
Yeah, if it's n, it would be connected to these points over here. So x is not adjacent to anything here. The only points it could be adjacent to are in this blue blob. And how many vertices are in this blue blob? This blue blob is not a technical term. It's just Okay, so there are fewer, less than or equal to n over 2 vertices in here. So what's the degree of x? What's the maximum possible degree of x? X is not adjacent to itself. N over 2 minus 1. So the degree of x is less than or equal to n over 2 minus 1. It might be much less. We don't know how big this blob is. But that's certainly an upper bound on the degree of x, which I'll note is equal to n minus 2 over 2. Oh, wait a second. But what did we say the minimum degree of the graph is? Okay, so we're assuming that the minimum degree is greater than or equal to n minus 1 over 2. And now we've shown that if it's not connected, if there's at least two blobs, then the degree of any vertex in here is less than or equal to n minus 2 over 2, which is a contradiction. Is that clear? So what did we contradict? What assumption did we make? Do what? Okay, so the assumption was that G is not connected. Okay, so what did we just prove? If the min degree is at least n minus 1 over 2, then G is connected. This is important. G is connected. Okay, I know we want to move towards this idea of Hamiltonicity, of finding a Hamiltonian cycle. I'm going to move up to that by starting with if the min degree of G is greater than or equal to n minus 1 over 2, then G is traceable. In other words, there's a Hamiltonian path. Okay, so and now we need to get into the nitty-gritty of proving something like this. So one more time, if the min degree is greater than or equal to n minus 1 over 2, then G has a Hamiltonian path. And again, I'm going to prove it by contradiction. Suppose not. Okay, so I understand n could be large, and we might have a lot of edges. Well, we certainly have a lot of edges. That's every vertex has nearly half is adjacent to nearly half the others. I can spend a lot of time. I can find a longest path. Okay, so it takes me a while, but I find a path, and it's the longest one. Okay. Okay, so here's the longest path. X. I'm just going to put some points here, and I'm going to put some points here, and it ends at Y. Now, if that has all the vertices on it, then I'm done. Okay, because if this blue path contains all the vertices, if there's all the vertices on this blue path, then G would be traceable and we'd be done. Remember, traceable just means that I have a Hamiltonian path, a path that contains all the vertices. So we're assuming that it's not traceable at this point. So what should we call it? X, Y. Oh, here's the point Z. Z is not on that path. But I have a graph with min degree n minus 1 over 2. And what did we show for a graph with min degree n minus 1 over 2? What? Someone said it. Connected. The graph is connected. So in fact, I know that there's a path from Z to the blue path. So I'm cheating. Oh, let's imagine that. We find, so there must be some vertex not on the path that's adjacent to that's adjacent to the path, the blue path. Okay? Is everybody with me at this point? Because I'm going to draw it again. All right, so remember this picture, and let's come back over here. Now what I want to do, here's my x, here's my y. What do I know the degree of x is at least how much? N minus 1 over 2. Degree of y is at least how much? Okay, so here's what I want to do. I want to look at all the adjacencies of x. Let me put a path in the middle, just for the heck of it. Here's some more points. It's a lot of points. Here's an edge. X is adjacent to that vertex right there. You can give it a name. Now let's look at y, and just so that I have something I can name it, let's look at the predecessor of u. Okay, so let's look at this point right here. Okay, what can you tell me about y and u minus? What can you tell me about y and u minus?
They can be adjacent
Why not?
because if they're adjacent, then you can go around.
Okay, wait a second. If they were adjacent, that's great. Okay, if y was adjacent to u minus, then what would happen?
You could start at the one before u minus.
Okay, the one, like right here, okay.
Go backwards to x.
Go backwards to u,
Go to u,
go to y,
and then
go here,
and you'll hit,
and what's wrong with that?
you'll hit z at some point.
Okay, no, z is off the path. Okay, it's a cycle, and what do we know about a graph with min degree n minus 1 over 2? What do we know about this point z? It must be adjacent to something on the path. One more time, we showed that if we have min degree n minus 1 over 2, then the graph is connected. If y is adjacent to u minus, one more time, I'm gonna draw the picture. I come down here, I go from u minus down to y, all the way down to u, and come down here, and now I'm gonna reshape that. That looks like this. One more time. I go down from x over to here, down to y, down here, and back here. So this contains all the original blue points. And what do we know about a graph with min degree n minus 1 over 2?
Connected.
It's connected. So in fact, z would be adjacent to that. But I started with the longest path. We chose a longest path from x to y. Here would be a longer path. Z to this point, all the way around to this point right here. Okay, so that's a contradiction. Okay, so one more time, y can't be adjacent to any point, any predecessor of an adjacency of x. Y is not adjacent to itself. Y is not adjacent to itself. We're not allowing loops. Okay, one more time. Y is not adjacent to any predecessor. Y is not adjacent to itself. So how many adjacencies of x are there? How many adjacencies of x are there? N minus 1 over 2. So n minus 1 over 2 gives me n minus 1 over 2 points that y is not adjacent to, plus 1. The 1 comes from itself, y. So it's not adjacent to, this is, let's see, n plus 1 over 2, and it's not adjacent to z. It's not adjacent to z. So y is not adjacent to n plus 3 over 2. Y is not adjacent to n plus 3 over 2. Wait a second. If y is not adjacent to n plus 3 over 2, how many points could it be adjacent to? What's the total number of points? What's the total number of points in this graph? N. So it's not adjacent to n minus n plus 3 over 2, so it's adjacent to at most how many? So the degree of y would be less than or equal to n minus n plus 3 over 2. And what is n minus n plus 3 over 2? This is algebra now. N minus 3 over 2. But what did we say the degree of every vertex is at least? Okay, but this has n minus 3. So that's a contradiction. Okay. So in fact, we know that y is not adjacent to any of these. So in fact, z can't be off this graph. Well, wait a second. If z's on this, if every point is on the blue path, then what must be the case? One more time. All the vertices lie on this blue path. So I know that I can't have a vertex off this path. Then all the vertices must be on the path. So z is on the path. So what do we call that? So the graph must be traceable. Okay? So in fact, what I've shown is that if we have a graph with min degree n minus 1 over 2, all the vertices lie on the longest path. Okay, so now I have a condition. It's not the best condition, but it is a condition. Let's show that it's tight. So n minus 1 over 2, if I take a complete bipartite graph, n minus 1 over 2 is as good as I'm going to get if I take n minus 2 over 2 and n plus 2 over 2. N minus 2 over 2 and n plus 2 over 2 is how many? The sum of these is n. Okay, so here's a graph on n, and we're going to put all these edges here. I'm going to put all those edges here. I have min degree down here is n minus 2 over 2, and this is not Hamiltonian. This is not traceable. So you should think about, let's see, this would be, for example, 2, 4. Okay, that's not traceable. Okay, so in fact, n minus 1 over 2 is the best possible. Now we have a way of telling when a graph is traceable. This is not an if, unlike the Eulerian property, this is not an if and only if statement, because we can have a max degree of 2 and the graph could be traceable. We can have a max degree of 2 and the graph be Hamiltonian. Just so you understand, we're a long way from 2. So we have to be sure that the degree gets up to, in this case, n minus 1 over 2, just to have a Hamiltonian path. Okay, so the next, one more step. We have traceable, I have connected, I have traceable. I want this Hamiltonian. So here's the theorem that they present in the book. They talk about in the book. This is by Dirac in 1952. And it finally gives a condition that implies when a graph is Hamiltonian. Notice we have a condition that implies the graph is traceable. That's close. Now we need a condition that implies that a graph is Hamiltonian. If G has min degree greater than or equal to n over 2, then G is Hamiltonian. And the proof is essentially the same. What do I mean by the proof is essentially the same? Okay, so I'm going to assume that G is a graph and it has min degree n over 2. And what I know is n over 2 is greater than n minus 1 over 2, so G contains a Hamiltonian path. Okay, so I have a Hamiltonian path. So the nice thing about a Hamiltonian path, it's all the vertices. The squiggle means that there are vertices, right? So I'm going to pick a point, and sort of pick a point in the middle. It has a Hamiltonian path, no vertices off this path. First of all, before I forget, so I want to actually assume, to the contrary, assume G is not Hamiltonian. So there is no Hamiltonian cycle. G is not Hamiltonian. But by the previous result, we know that it contains a Hamiltonian path, so G is traceable. So there's a Hamiltonian, all the vertices are here. All of them are here. So I'm going to do essentially the same idea. So I have a Hamiltonian path, starts at x, ends at y. And now what can you tell me about this edge? That green dotted thing. What can you tell me about that? Okay, one more time. It's not Hamiltonian. Can this be an edge? Why not?
Then it'd be Hamiltonian.
Okay, wait a second. If this was an edge, where do I go? What do I do?
Over to Y.
Okay, wait a second. I take the green dotted thing. I follow the path down to y. I take this edge over to here, and I go all the way back down to x. And that would be a cycle. A cycle that contains all the vertices. So if this is u, and let's call this u plus, if y is adjacent to u, if yu is an edge, then, let's see, then x u plus is not an edge. Okay, so how many non-edges are there? Let's see. So how many edges, what's the degree of y? What's the degree of y? What are we all? So what's the degree of y? At least n over 2. So let's see, that means that there are at least n over 2 vertices that x is not adjacent to. The degree of y is greater than or equal to n over 2. So there are at least n over 2 vertices not adjacent to x. Okay, let's see, what are those? It's all of the successors of adjacencies of y. So every time y is adjacent to something, x is not adjacent to the next one. So y goes to another point, x is not adjacent to that. So that gives me n over 2 vertices not adjacent to x. I need one more. Because if I have n over 2 not adjacent to x, and I have one more, that would be n over 2 plus 1. If I had n over 2 plus 1 vertices not adjacent to x, then what would be the maximum that the degree of x could be? No? Okay, one more time. There's a total of n vertices. I know that there are n over 2. Those are the successors of adjacencies of y. So I know that there's at least n over 2 vertices not adjacent to x. If I can find one more, that would give me n over 2 plus 1 vertices not adjacent to x. Let's see, n over 2 plus 1 vertices not adjacent to x. What's the total number of vertices in this graph? N. I have n over 2 plus 1 not adjacent to x. So what would be the maximum that I could have adjacent to x? Okay, if I could find one more, if I can find n over 2 plus 1 not adjacent to x, this would be a contradiction because this would imply that the degree of x would be less than or equal to, and I'm going to write it as n minus n over 2 plus 1. N minus n over 2 plus 1 is better known as n over 2 minus 1. Oh, but if the degree of x is less than or equal to n over 2 minus 1, then this is a contradiction. I'm not done yet. I need one more point that's not adjacent to x.
X.
Ah, there we go. X is not adjacent to x. So we have all of the successors of adjacencies of y, and there's n minus 1 over 2 of them, n minus 1 over 2 of them, and then we have x is not adjacent to x. So I have n over 2 plus 1 vertices not adjacent to x, which would imply that the degree of x is less than n minus n over 2, which is n over 2 minus 1, which is a contradiction. So in fact, that's the assumption that we just contradicted. Okay, now, again, these are sort of the foundational results related to the idea of finding long cycles and long paths. So we started with connectivity, Hamiltonian path, Hamiltonian cycle. Now, unfortunately, it still requires a lot of edges. And for Hamiltonicity, you're not going to be able to get away with anything much less than that. So that's the sort of the disappointment of looking at these Hamiltonian graphs or looking for Hamiltonian cycles versus an Eulerian graph where it's open and shut. Questions about this? I mean, this argument is going to come back as we move on in the course of this semester. We're going to look at similar sorts of arguments to actually do a lot more counting. So we're going to count to come up with different structures about the graph. Okay, so I want to mention one more thing. So I've got a degree condition that implies connectivity. I have a degree condition that implies traceability. I have a degree condition that implies that the graph is Hamiltonian. So one more. I'm not going to prove it. But I don't have to go up too much more to get a rather strong property. So a graph is Hamiltonian connected. Okay, connected, that we've known connected for a long time. Traceable Hamiltonian path. Hamiltonian meaning a Hamiltonian cycle. Hamiltonian connected means that if I close my eyes and I pick any 2 points, okay, close my eyes, I pick any 2 points, there's a Hamiltonian path starting at one and ending at the other. A Hamiltonian path meaning all the vertices are on that path. Hamiltonian connected means that for all x and y vertices in the graph, there is a Hamiltonian path that starts I'm putting quotes around starts because there's no direction, but starts and ends at X and Y, respectively. So it's so dense, I have so many edges, I can choose any two of them, and I can find a path that contains all the vertices from X to Y. Any guesses on how big this would be? How big the degree would have to be? And this is what I hope you find surprising. In fact, so let's see, we got n over 2 is connected, n minus 1 over 2 is connected and traceable, n over 2 is Hamiltonian. And to get this Hamiltonian connected, I hope you appreciate, this is, I means I can go from any one vertex to any other vertex and find a Hamiltonian path containing all the vertices in the graph. If the min degree is greater than or equal to n plus 1 over 2. So we're almost there. We're almost there with Hamiltonicity. Just one half more. If the min degree is at least n plus 1 over 2. So we get, and you should appreciate how much stronger this is, that I can go from any one vertex to any other vertex. By the way, Hamiltonianness, the fact that there's a Hamiltonian cycle is immediate, right? I choose an edge, x, y. This says that I have a Hamiltonian path that goes from x to y. And it can't contain the edge x, y because those are going to be the starting and ending points of this path. So in fact, once we have something like this, the proof for Dirac becomes a little bit easier. Okay, so it's pretty simple. They talk about this in the book, and they look at the relationship between Hamiltonian graphs and some of these other properties. Okay, we're not going to worry about these cut sets, but I still want you to be looking at several of the examples that we looked at last week. I gave you five problems from chapter 5. Okay, some of them deal with Cartesian products. We've looked at PM cross PN. One of the questions asks about G cross H. Sorry, G box H. I draw it as a box and I still say cross. Okay, so it looks at some of the products, and it'll give you some things to play with. I wouldn't want you to have a boring break. So just to give you, just to let you know, on page 235, they introduced the idea of Hamiltonian connected, which is this, that I can get a Hamiltonian path. For any 2 points, there's a Hamiltonian path from X to Y. So you may want to look at that. We're not going to spend much time, but in particular, what we are going to do is, once we come back from break, we're going to begin looking at levels of connectivity. So the next chapter is called Connectivity. I think that's the title of it. Yep, chapter 6 is Connectivity. And I just want to quickly start by giving you something to think about over the course of your break. I know you got all this to think about, but if you look at page 237. Here are 4 graphs on page 237. I know you can turn to that page, but I want to actually draw them up. Tell me what it means to be connected. We better know, because I proved something about it. What does it mean to be connected?
Every vertex has a path between it and another vertex.
Okay, so for connected means for any 2 vertices x and y, there's a path from x to y. I don't care how, it's not a Hamiltonian path necessarily. Okay, but it's at least a path. So here are four graphs on 5 vertices. And the last one is. Okay, so here are 4 graphs on 5 vertices. I understand that the number of edges are different. But, you know, as you look at these graphs, what can you tell me about how connected they are? What can you tell me? Let's look at that first one, sideways F. How many vertices do I have to remove to disconnect sideways F? Everybody understands what I mean by sideways F, right? 1. Okay, in fact, there are 2 ways to remove 1 vertex. So if I remove this vertex, or I remove this vertex, the graph is disconnected. Now, as we imagine that this is an applied area of mathematics, it could be, in some places it's an applied area of mathematics, we might think of our graphs as transportation networks. Or we might think of them as ways to distribute products from one place to another. Or we might think of them as strategic designs for certain defense systems. And this is really what happens. And what I want to be sure, if I look at sideways F, notice if I'm the enemy, and I want to disconnect the American, let's say these are communication networks, and I want to disconnect the American communication networks, how many points, how many transmitters do I have to blow up? Okay, I don't mean to be morbid. Okay, if I blow up one of those 2 that I circled, then in fact my communication is broken. Okay, so this is this idea of connectivity and how many points you have to remove to disconnect the graph starts to look at the vulnerability of a network. Okay, what's the case for the C5? Okay, so notice in the C5, if I remove 1 vertex, the system is still connected. And assuming that I have adaptable communication networks, I can still communicate. Of course, the one that's been bombed, there's not much I can do, but everybody else, the ones that still exist, I can communicate from one to the other. But if I remove, there is a way to disconnect the graph by removing, let's not use bombing, by removing 2 of those. Is that clear? What about the square with a point and a vertex in the middle? Okay, so one more time. Remove 1. Remove 1 to disconnect. Remove 2. Now, it's not any one, right? We have to be strategic about it. We have to remove the right one. If we bomb this one, if we remove this one, the remaining points are all connected still. So I have to choose the right one. Here, if I remove 2, and I have to choose the right 2, then the system is disconnected. The resulting graph is disconnected. Here, if I remove how many? 3. So here I have to remove 3 to disconnect the graph. And for the complete graph, in fact, we really can't disconnect it. If I remove 4 vertices, then the graph remaining is just one vertex, and in essence, it's still connected. So this is the, no, it's not possible to disconnect this graph. Okay. All right, so chapter 6 moves into studying this idea of connectivity. And looking at, if I increase connectivity, what does that tell me about the structure of the graph? Of course, we're not going to have 5 vertex graphs to just worry about. We've got to worry about n vertex graphs, 100 vertex graphs. Okay, so what I'd like you to do is be looking at 6.1 and 6.2. Let me back up for a second. So not only, let's go back. Everybody, is it clear how I'm going to disconnect by removing a vertex? Is that clear? So what's the, and now let's talk about strategic planning, and these are roads. And I want to disrupt your transportation. So I'm looking at F, sideways F. How many roads do I have to blow up? How many edges do I have to remove to disconnect the graph? 1. If I pick the right one, I can, oh, in fact, here it's in F, in the sideways F, if I remove any edge, then the graph is disconnected. And remember, I'm just removing the edge, I'm not removing the vertex. So again, this is a strategic maneuver. So we talked about vertex connectivity. Now we're going to start looking at edge connectivity. Vertex connectivity, what's the fewest number of vertices I have to remove to disconnect the graph? Edge connectivity? If you had to guess. So vertex connectivity, fewest number of vertices removed to disconnect. Edge connectivity, fewest number of edges. And I'm just going to put edges here. Fewest number of edges you have to remove to disconnect. Okay. And as we move into chapter 6, you'll see that we actually define what it means, what the vertex connectivity means, and the edge connectivity as being the minimum number of vertices that I have to remove to disconnect the graph, and the minimum number of edges. And just to sort of torture you just a little bit longer, how many let's take Kn. Okay, Kn. What's the minimum number of vertices that I have to remove? Oh, let's look at K5. What's the minimum number of vertices that I have to remove to disconnect the graph? In fact, K5, you can't disconnect it. If I remove 1, it's still connected. Remove 2, it's still connected. 3, it's connected. 4, it's connected. And I guess you could remove 5, but then you got nothing. And I guess nothing's connected. So the complete graph is the least vulnerable to vertex attack. But I can disconnect it by removing edges. What's the smallest number of edges I can remove to disconnect, in this case, K5? 4. So I would isolate a vertex. So I would remove all the edges at a particular vertex. There are other ways to disconnect the graph, but 4 is the smallest number of edges. So you might want to think about how vulnerable certain graphs and certain graph structures are. They just love to give you little problems to work on. So you'll see at the bottom of page 238 and 239, here are some graphs, and you want to try and find what the vulnerability, what the edge and vertex connectivity is. What's the smallest number of vertices to disconnect the graph on the bottom of page 239? What's the smallest number of vertices for the graph on the bottom of page 238? Let's take a minute before we wrap this up. Let's just look at those two graphs. Hey, this isn't easy. It's kind of like Hamiltonicity. It's not easy.
A4应该是移动的这个点，我这个是 ACV 的因为是我 B 和 U 的不连着。
I'm not going to draw these. So let's just 6.2.1. What's the fewest number of vertices that you have to remove to disconnect this graph? Okay, well, can I just remove one? I can? No. So I'm on, again, I'm on page 238, 6.2.1.
So the first one, yes.
You can remove one vertex. Which vertex are you going to remove? This one right here?
Yeah.
One vertex.
可以啊。I saw it before.
Oh, the first question. Yeah. You play with the first question. One I, and I. You play with those. You're going to have a lot of stuff to play with. I'm looking at figure 6.2.1, not discussion 6.21. I just want to know what's the fewest number of vertices that I need to remove to disconnect the graph in 6.2.1. Can anybody disconnect it by removing one vertex? Two vertices? It's like an auction. 3 vertices? Okay, we got 3 vertices. So, and again, there's always a hard part of graph theory, unfortunately. We think the answer is 3. Now we have to prove that 3 is the minimum. Okay, so that's something for you to actually contend with over break. I know you're all looking for stuff to do over break. 6.2.2? Oh, I didn't worry about edges. You can worry about edges. We'll start with that when we come back. What about 6.2.2? And we haven't looked at the Peterson graph in a long time. got quiet.
这是可以记这个。
Oh, I can tell you're all gonna have a fun break looking at all of this graph theory. Is this mine? Michael? Yeah, I found it. I'm sorry, I
Oh, no
forgot.
problem at all. Thank you.
Ying,
上次有些人没拿这个。
而且这个不是因为
Selma,
手出来的一节日，
最少4个，
它最少的连的念最少的不会是这个吗？
Yu Yuan Gao? What's your English name?
English name?
You don't have an English name?
I don't have a English name.
Okay. You all make it hard on me. Song? Do I?
Yes.
And we make it hard on you. I know. Louis? Yang Cheng?
Yeah.
What's that symbol? Is that a
I have no
mistake?
idea. Yeah,
Okay.
it's a mistake.
Okay. I didn't know if that was your.
No.
Lou? Liu? Qin Shi Shen? Wang? CJ? Victor?
属于红色的分水口，所以
Pam? Connor? Sarah? Jinwen?
你这个象棋其实无所事事，我这个大家都看过。
无所事事的定义是我就不知道出来的。
Okay,
没错，无所事事就是没有办法玩。
Ying, I know some of you didn't get your test.
不能玩这个游戏。
Michael?
来，你要去考公。
Ying,
跟那你要跟
let's try this again. I know V's not here.
我看考出有什么红色的狐还是蓝色的狐？
哎，快点问我那批的。
John Wen? John Wen Liu?
He's not here.
He's not here. Ji Yuan Yu.
不是你吗？
Ji Yuan Yu. Is that an L or a... Okay, what is that? What is that? Oh, there's an L there. L-Y-U? Okay. Qinwei Wang?
对吧？你还分不清自己的名字已经发音。你看。
Did everybody get one? Hopefully
沈秋实
their own?
每次我从来没去老师
Okay.
课上发一个名字，就是你。是啊，你看他每次都能分辨。
Okay, how you coming on those? How you coming? All right. Have a nice break. Okay, and remember, there's homework due right after break. Okay. Yeah.
Do right after break.